A commercial jet is climbing through 6,600 feet in complete darkness. The autopilot is engaged, engines are nominal, and flight parameters appear completely stable. The captain's display triggers an overspeed alarm, surging past 350 knots, warning of structural disintegration. But simultaneously, the first officer's display shows speed plummeting below 200 knots. The control column shakes violently, warning of an aerodynamic stall. This is an impossible data state. A machine is simultaneously reporting that it is tearing itself apart from excessive velocity and falling out of the sky from a lack of it. To resolve this contradiction, we must examine the exact mechanism of a catastrophic systems failure, a moment where analog physics, rigid automation code, and cockpit hierarchy fatally collided. This is the exact scenario that unfolded on February 6, 1996, on board Birgenair Flight 301, a Boeing 757 departing Puerto Plata in the Dominican Republic. Inside the cabin, 189 passengers and crew settled in for the long flight to Germany, completely unaware that their aircraft's sensory network was already compromised before the engines even started. This impending hull loss originated from a localized, microscopic sensor anomaly that effectively bypassed every redundancy protocol on the aircraft. To understand the crash, investigators worked backward from a doomed, chaotic flight deck to this, a 2-inch metal cylinder called a pitot tube, left exposed to the elements on a tropical tarmac. And that requires examining the specific physics of how a simple analog sensor actively lied to a digital computer. This diagram illustrates the mechanical function of a pitot-static system. It calculates airspeed by measuring the mathematical difference between the incoming ram air pressure at the front and the ambient static air pressure at the side. Flight 301's aircraft had been parked at the airport for 25 days. During that time, standard maintenance procedures required protective covers to be placed over these tubes. They were never installed. This exposed the aircraft to a highly specific local biological threat, the mud dauber wasp. This species instinctively seeks out dark cylindrical holes to build its highly compacted mud nests. The wasp nest hermetically sealed the captain's pitot tube at ground level. This permanently trapped a mass of sea-level air pressure inside the front chamber of the sensor. When the aircraft took off and began its climb, the outside static pressure dropped as the air thinned out, but the trapped ram air pressure remained artificially high. According to the equation, if static pressure decreases while total pressure stays fixed, the calculated airspeed climbs. The mechanical blockage did not result in a dead sensor outputting a simple zero in flight. Instead, the laws of thermodynamics forced it to act like an altimeter, actively generating false, continuously accelerating data the higher the plane climbed. This diagram maps the expected redundancy of a Boeing 757. The aircraft is equipped with 3 independent pitot tubes, each routing data to 3 isolated air data computers. But the 1996 autopilot software contained a critical logic flaw. It was hard-coded to default blindly to the captain's air data computer without any automated cross-referencing against the other 2 sensors. Fed exclusively by the blocked pitot tube, the autopilot believed the aircraft was hurtling past 350 knots. Attempting to prevent structural breakup, the computer forcefully pitched the nose up and throttled back the engines. The computer was successfully recovering a virtual aircraft from an overspeed condition, but in doing so, it was driving the physical aircraft directly into an aerodynamic stall. Hardware redundancy means nothing if the underlying software architecture relies on a single, unvalidated data stream to execute automated physical actions. When faced with conflicting speed data, pilots are trained to execute an unreliable airspeed procedure. This requires instantly disconnecting the autopilot, applying full engine thrust, and flying based on known pitch angles. But inside the cockpit, Captain Erdem was experiencing severe sensory overload. Bombarded by the blaring overspeed alarm and confused by the contradictory warnings, he actually pulled the thrust levers back even further. This response highlights a concept known as the authority gradient. There was a massive experience gap on the flight deck. Captain Erdem possessed nearly 25,000 total flight hours, while First Officer Gergen had a mere 71 hours on the Boeing 757. The first officer's isolated instruments were not corrupted. They accurately reflected the imminent stall. Cockpit voice recordings confirm he repeatedly verbally warned the captain that their speed was critically decreasing. Both pilot seats on a 757 have active controls. Despite knowing the aircraft was losing lift, the first officer's junior status and the rigid cockpit culture paralyzed him. He failed to physically seize the flight controls and push the nose down. The blocked sensor and flawed software alone did not doom the aircraft. The fatal variable was the psychological hierarchy that silenced the only crew member possessing the correct beta. Just 5 minutes after takeoff, Flight 301 stalled entirely. It plummeted nose first into the Atlantic Ocean, resulting in a total hull loss. All 189 people on board were killed. Finding definitive proof of the system failure presented an immense logistical hurdle. The flight recorders were resting at an inaccessible depth of 7,200 feet on the ocean floor. The U.S. Navy deployed a specialized, remotely operated vehicle, the Curve system. After a painstaking 22-day underwater mission, they recovered the units. When the data was extracted from the flight data recorder, it mathematically confirmed the exact moment the pitot tube transformed into an altimeter. The telemetry perfectly aligned with the confusion captured on the cockpit voice recordings. The recovered data provided undeniable, raw telemetry that exposed a lethal oversight in the core philosophy of glass cockpit design. Regulators forced Boeing to redesign their flight deck interfaces. They mandated the addition of a prominent, unignorable instrument disagree warning to immediately alert crews whenever sensors fall out of alignment. Global simulator training was rewritten to include mandatory, unreliable airspeed drills. Crew resource management protocols were restructured worldwide, specifically training junior officers to forcefully challenge captains in critical situations. Birgenair 301 remains the ultimate systems engineering cautionary tale. It proved that the most sophisticated automation is lethal without data validation, and the most experienced crew is doomed if hierarchy suppresses the truth.